Welcome to the Eurofins E&E webinar on certifying medical electrical equipment to standard IEC 60601-1. If you have any questions about the information provided, please send an email to marketing@metlabs.com so we can put you in touch with one of our specialists. This webinar will cover the major aspects of certifying medical electrical equipment to IEC 60601-1. We will begin with the concept of a patient and essential performance. Then we will touch on the testing aspect, which is only a part of what it takes to certify medical electrical equipment. Next, we'll discuss the risk management file, what it is, why it's necessary, and what goes into it. This is the cornerstone of certifying medical electrical equipment, so we will spend more time on this topic. We'll also examine the requirements for Programmable Electrical Medical Systems, or PEMS, and the collateral standards on usability 60601-1-6 and alarms 60601-1-8. Let's dive in and take a few minutes to discuss the concept of a patient and why so many aspects of the medical standard are more stringent. A patient is defined as a living being undergoing a medical, surgical, or dental procedure. Patients can have some specific characteristics which make them different from the average person. Here are 4 examples. First, a patient may have open skin. Skin is a good electrical insulator. Open skin can conduct more current. Second, a patient may be unconscious and unable to react to pain or call for help. Third, a patient may be immobile and unable to move from pain. Lastly, a patient may have a suppressed immune system, which makes them more susceptible to germs, dirt, and allergic reactions. Now that we've discussed the patient, let's talk for a moment about the aspects of medical electrical equipment that can harm a patient. First, we'll discuss leakage current. All electrical equipment has leakage current, even low voltage equipment. This current can travel from the surface of equipment through a person to the ground. Current generally goes from line to neutral, or from positive to negative for a battery. However, there is some leakage current that does not go through the loop. It may go through the ground wire, or it may be present on the surface of the equipment. It is accessible to anyone who touches it. If a high leakage current were to pass through the heart to the ground, it can cause death. The patient in this scenario is more susceptible because they can't call for help and can't move away. Let's look at that for a moment. Any amount of current over 10 milliamps, or 1/10 of an amp, can produce painful to severe shock with muscular contractions that are so strong the victim cannot let go of the wire that is shocking them. At values as low as 20 milliamps, breathing becomes labored, finally ceasing completely, even at values below 75 milliamps. As the current approaches 100 milliamps, ventricular fibrillation of the heart occurs, an uncoordinated twitching of the walls of the heart's ventricles, which results in death. Without proper isolation from the high leakage current, a person can die, and the patient with open skin, who may be unconscious or bedridden, is more susceptible, can't call for help, and can't move away from equipment with high leakage current. Now let's talk about temperature. Higher temperatures burn the skin faster. Our body temperature is 98.6 degrees Fahrenheit or 36.1 degrees Celsius. Faucet water causes pain at 110 degrees Fahrenheit or 43 degrees Celsius. And the skin can burn with prolonged exposure to 120 degrees Fahrenheit or 48 degrees Celsius. Burns will also occur with a 30-second exposure to 130 degrees Fahrenheit or 55 degrees Celsius, and with a 6-second exposure to 140 degrees Fahrenheit or 60 degrees Celsius. Most adults will suffer third-degree burns if exposed to 150 degrees Fahrenheit or 65 degrees Celsius for just 2 seconds. In the event of overheating equipment, the patient is more susceptible and may not be able to call for help or move away. Lastly, there's biocompatibility. This is the quality of a material that enables it to touch a patient, skin, tissue, or bone without a toxic reaction or immunological rejection. Patients with a depressed immune system are more susceptible and unable to fight off a toxic reaction. Toxicity can impair major systems in the body and can spread away from the point of contact, so that it is difficult to realize that the body is being attacked. The patient is more susceptible with a depressed immune system. A toxic reaction may cause death. If a part of the equipment that touches the patient is made from a material that is toxic, the patient is more susceptible and can't call for help or move away. As a result, the medical standard IEC 60601-1 has a concept called the applied part. This refers to the part of medical electrical equipment that touches the human body. Examples of this are a blood pressure cuff, an operating table, the sensor of a multi-parameter monitor, or the leads of a defibrillator. If the equipment is used around the heart, it needs to have the most isolation from electricity possible. This is the type CF applied part. If the equipment applies electricity to the human body, it must have sufficient isolation to float. This is the type BF applied part, and everything else can be a type B applied part and may be earthed or have a lesser isolation than a CF or BF applied part. There's also a special category of applied parts, defibrillation proof. These parts will not conduct the current caused by a defibrillation shock to the rest of the body. The standard places special requirements on applied parts: lower leakage current limits, lower temperature limits, and biocompatibility requirements. Switching gears, let's discuss the next concept that is particular to medical standards, and that is essential performance. Essential performance is performance of a clinical function other than that related to basic safety, where loss or degradation beyond the limits specified by the manufacturer results in an unacceptable risk. We'll be covering unacceptable risk in depth later, but simply think of it as the possibility of minor injury all the time, severe injury fairly often, or quite possibly the instance of death. Here are some examples of medical electrical equipment with essential performance: a defibrillator, a respiratory monitor, an insulin pump, or a heart monitor. In each case, if the equipment stops functioning, the patient can be harmed. Not all medical electrical equipment has essential performance. A hearing aid, for example, may not have essential performance. The patient is not harmed if the hearing aid fails. In summary, the medical standard requires that, after we perform our electrical and mechanical tests, not only must the equipment stay safe, it must also continue to function if it has essential performance characteristics. So now let's talk about testing. If you have ever certified IT equipment, lab equipment, or certified medical electrical equipment to the standard from the 1990s, a lot of the tests in today's medical standard are very similar. Sometimes, though, they are more stringent. Examples include marking durability, which requires more chemicals, accessibility, which requires a test hook, and cap discharge, which requires a faster decay. Here are some more tests which are virtually the same. And then there are some additions, such as the temperature limits of applied parts. Any part of medical electrical equipment that touches the patient and exceeds 41 degrees Celsius or 105 degrees Fahrenheit must be documented in the manual. Nothing can exceed that temperature limit for long periods of time. Even parts that can be touched by an operator have special limits. Leakage testing is very special for medical electrical equipment. As we discussed earlier, patient leakage is the current that can pass from an applied part through the patient to the ground. Patients with open skin are more susceptible to leakage current. For this reason, many components of medical electrical equipment are designed to be electrically isolated. And to verify this, we perform numerous patient leakage tests. We may measure up to 6 different combinations of electrical situations to make sure that current cannot harm the patient. First, we measure the leakage that goes through the ground pin and the leakage that is on the surface of the equipment or applied part that doesn't go into the ground pin. Then we measure leakage that may come from other pieces of equipment that we can't control, and we cover leakage from metal that has no path to ground. Finally, we measure leakage from signal ports that can't be controlled, the cumulative effects of leakage from several points, and from point to point when more than one part of the equipment touches the patient. And there are some tests that are new and specific to medical electrical equipment, making sure that rolling equipment does not tip over or stop functioning. making sure that equipment can support 2 to 8 times its expected load, being able to read the label from a distance, making sure equipment is restored to safe state after a power outage, making sure equipment that is already connected to the body still works after a shock event, making sure equipment cannot be turned up beyond safe limits, making sure that equipment won't spark in an oxygen-rich environment, and making sure that the material of the applied part does not cause toxic reactions or immunological rejection. Now let's discuss the risk management file, which is the heart of the certification process for medical electrical equipment. The third edition of IEC 60601-1 was released in 2005 with a special process called risk management. The basis of the concept is to address the realities of medical electrical equipment. First, no standard can cover all the aspects of medical electrical equipment. Next, the standard cannot address whether a hazardous aspect of the product might be acceptable within the industry. Lastly, because essential performance is different for different equipment, the standard cannot define how to test for it. So the risk management process was developed to provide a systematic method for addressing safety and essential performance testing that goes above and beyond what the standard includes. The risk management process is defined in ISO 14971, Application of Risk Management to Medical Devices. The risk management process starts with a plan that is very high level. What knowledge and resources need to be brought to the design and development process? What is acceptable or unacceptable if the product causes harm to the patient? How will the concept of unacceptable risk be evaluated throughout the design and development process? Unacceptable risk is a combination of how bad and how often. As part of the risk management process, at the management level, there is a determination of unacceptable risk. The first half is a determination of severity levels. Examples of these include death, a stroke, a broken bone or hemorrhaging, a cut, or a stubbed toe. This is the easy part. Next is a quantification of how often something can occur. More than 1 in 1,000 or less than 1 in a million. It takes extensive research to determine probability, typically from medical journals, data gathering studies, and competitor equipment. These two quantities are then combined into a matrix. This is unacceptable risk. We want to point out that in this particular chart, less than a 1 in a million chance of death has been deemed acceptable, while stubbing your toe frequently is unacceptable. This is a point for management to decide. Here's a slightly different chart. Here, even improbable risks are reviewed to see if somehow the risk can be reduced. There are 7 basic steps to the risk management process that is performed by the technical team. The first 3 constitute risk analysis. Number 1, define the intended use, characteristics, and essential performance of the product. Number 2, identify the safety hazards inherent in the product at the concept stage. Number 3, identify faults, hardware, software, physical design, or component selection that could cause a compromise of the basic safety or essential performance. Number 4 is risk evaluation. Estimate the risk and determine if it is acceptable. If not, number 5 is risk control. Design, protective measures, and information for safety. Number 6 is residual risk. Review the design for risk that may still be present after risk control. If there is residual risk, go back to step 4. Number 7 is risk-benefit analysis, a management decision of whether to pursue a project where the equipment has residual risk that can't be eliminated. Annex C of ISO 14971 is very helpful in beginning the process of identifying hazards. It has 34 questions, each with subclauses. Many manufacturers use it as a yes-no questionnaire, but it is much more than that. It is a guideline for identifying hazards created to go beyond the 60601-1 standard. Here are some examples of the issues that Annex C touches on to help identify hazards. Using the characteristics of the equipment, the hazards are identified. Here are examples of 5 products and 5 very different potential hazards: biocontamination, electric fields, usability, software error, and environmental concerns. When there is a hazard with unacceptable risk, there are 3 ways to control the risk. The first is with an inherently safe design. If the design can't be made safe, there is the protective measure. This can be hardware or software. For example, a use indicator, software checks, or temperature monitoring. And sometimes, even the protective measure is not possible, and the only risk control measure is a label, instruction, or warning. Once you have iterated the process, all unacceptable risks should be eliminated, but that is not always possible. This is when the management weighs the risks against the benefits. Here are 3 examples where the treatment method is so beneficial that the possibility of death or unacceptable harm is acceptable. The risk management file is the documentation of how the equipment was designed and developed so that all its inherent risks were identified, analyzed, weighed, eliminated, or accepted. It also includes a matrix of how the safety agency should be testing to ensure that safety and essential performance are considered. Now let's switch gears and talk about programmable electrical medical systems, or PEMS. PEMS can be software or firmware. They represent any programmable aspects of the equipment, and if safety or essential performance depends on it, we must investigate it. Here are some quick examples. Software that prevents excessive output or controls a critical function. Most safety engineers are not experts on software, so we rely on the software designers to demonstrate that they followed a regimented development process and that the subsystems that control aspects of safety and essential performance get special attention. Risk control is the process of taking measures to reduce or eliminate the potential for harm to the patient, operator, or environment through design changes or protective measures. There is a special standard, IEC 62304, that defines the lifecycle process for software development and changes. This, in combination with Chapter 14, defines the architectural aspects of the software that should be considered, how the subsystems should be designed, how the aspects that the software controls are managed, and how the software is tested. The lifecycle process is generally very familiar to software engineers. This is combined with the ISO 14971 standard, which defines how to design the software so that special attention is paid to how basic safety and essential performance are controlled. This part is not familiar to software engineers, and this is where the overall risk analysis and the software intended use intersect. This needs to happen at the beginning of the software development process, so that software design architectures are used to mitigate risks in software that controls basic safety and essential performance. Testing software for medical electrical equipment must be extensive. Individual components and integrated systems must be tested, and the test must be run by engineers who did not design the software, sometimes an independent company. There is also a section of the standard that addresses communication of the medical electrical equipment with other equipment or an IT network. The IT network is outside of the control of the equipment manufacturer. You can only put information in the manual of how to limit the IT network, and you can add hardware to limit potential leakage. Now let's talk about usability. The 60601-1-6 standard is required for the CB scheme. It is required by the FDA, and Eurofins requires it for a full product listing. Let's talk about why usability is so important. Use error is one of the biggest reasons why patients get hurt in medical environments. That can lead to a medical malpractice suit. Here are some other basic reasons why medical products have usability issues. Sometimes the only mitigations are training, labels, or the manual. So, a process has been developed to specifically design out use error and use-associated risks, and products must meet the usability specification. This is defined as a way of detailing the design requirements of the equipment such that a user can interact with it without error, even under adverse conditions. When a manufacturer uses the usability engineering process with their design at conception, the user interface of the product should be easy enough to use that error is unlikely, even in adverse conditions. This means that it meets its usability specification. This is demonstrated with a validation test. The validation test is meant to be comprehensive. It looks at every aspect of using the product and making sure that the operation is intuitive or easy with proper training. We're going to show you the process backwards and then step forward through it. The end state is a product that is unlikely to have use errors, and the manufacturer has done tests to show this or find design flaws that are fixed. The test is based on a plan for how the product can be used correctly. And correct use has been well defined in a usability specification, including things like how long it should take, how likely it is to get it right the first time with proper training, and how easy it is to handle. To define this specification, you look at all the steps in using the equipment, including those related to safety. This comes from the intended use of the product, as well as who, when, where, how, and why it is used. That is the application specification. Now let's step forward. The 62366 usability specification includes a very simple example, an electronic thermometer. And the first thing that is done is to establish what, who, where, when, how, and why. Next, you identify every step, small or large, that is required to use the equipment properly, including turning it off and on, removing and replacing the cover, and cleaning and storing. Here are the potential hazards. Some of them are pretty serious, even for something as simple as a thermometer. We talked about the usability specification. This is the specification of how easy it is to do each task without error and under the worst conditions. To show you how detailed the usability specification is, look at the design requirements related to the act of turning on or off the thermometer. The physical design is a major component in usability. Here, each aspect of the physical design makes the thermometer easy to use. From this comes the validation plan, the test environment, the test subjects, and the activities. At the conclusion of the validation activity, either the product is free from most possible use errors, or there need to be changes to the design, the protective measures, or the instructions. As you can see, there's a lot of detail that goes into a usability study, but it is a very orderly process. If done at the beginning of the design process, it can eliminate many headaches. When done at the end, it still may catch glaring problems. We want to end the presentation with some information about two collateral standards that we see frequently. The first is 60601-1-8 for alarms. The 60601-1-8 standard is designed to address all aspects of how alarms should be designed. This is accomplished by defining alarm categories or priorities by degree of urgency, consistent alarm signals, and consistent control states, and their marking for all alarm systems. It does not, however, give guidance on whether an alarm is needed. Many products have multiple alarms. A heart monitor, for example, will have an alarm for a low heart rate, but it might also have an alarm in case of a hardware fault. It might also have an alarm for a low battery. Alarms are prioritized, and their sounds and visual indicators are different so that a healthcare professional can tell instantly how quickly they need to respond to the alarm. Alarms have color requirements and flashing frequencies based on their priority. Alarms also have audio characteristics. A very special rhythm is given to a high priority alarm so that it is recognizable above the other sounds in a healthcare environment. Other clauses of the alarm standard have requirements for when the alarm is turned off, what defines when an alarm goes off, and whether an alarm can be silenced. The last topic we want to briefly cover is home healthcare, 60601-1-11. This standard is focused on equipment that is used anywhere other than a healthcare environment. It can be in the home, outside, or anywhere where there is no medical professional nearby. There are several things that make home healthcare different. The first is from a shock hazard perspective. The shock hazard protections in a hospital cannot be guaranteed in a home. Next is the fact that when patients are using the equipment, they may not be trained, and they most likely are not healthcare professionals. Their reading level is also unknown, and their likelihood of reading a large training manual is slim. Lastly, we look at the environment. Again, it is most likely an uncontrolled environment, especially as compared to a hospital. And here are some of the items the standard requires to mitigate these risks. Medical equipment in the home must not rely on grounding, especially since older homes may not have any. The product manual must be written to accommodate a range of education levels. And the product must be intuitive enough so that people who skim the manual can still use the product. How many people are going to read the manual for something as simple as a thermometer? To consider the environment, equipment is operated at the widest range of temperatures and various humidities to see if it still operates normally. Then it is exposed to high and low storage temperatures, shock and vibration, dropping, compression, smashing, and spilled water. After these tests, it may not work completely, but it must still maintain basic safety and essential performance. That brings us to the end of our presentation. Thanks very much for viewing this video. If you have any questions, send an email to marketing@metlabs.com. We will have a subject matter expert respond to you directly.